it blocks me from starting the recorder. And so I have to get all these little pieces in order. Okay, and it's not going from current slide. There we go. Before we get into example 5, let me just fill you in. I think you probably heard most of this before, but I may have found out some more stuff since then. This week is just an horrendous week. Um, my friend died. I'm having to make a lot of the arrangements. So most of my office hours this morning, I had 8 to 10 this morning, because I can't do a lot of this stuff after hours because no one's in the office then. So I have to do it during when they're in, and that's when I have office hours. So most of my 2 hours this morning were spent dealing with various things there. The next 2 hours I have from 4 to 6, I've got to go to the Episcopal place and meet a couple of people there, and we're going to clear out some of the stuff out of our apartment, and some of them are going to claim some stuff. There's somebody else who's involved with the ministry of our church that had a fire in her home Monday and lost about 90% of everything. So this looks like a good place that they can at least get some things to tide them over until that happens. So I have to be there to give permission for those people to go into the apartment. So that's happening. So as soon as my 3:45 class is over with, which Kira is in, I'm out the door on the way to Episcopal place. Hopefully I'll be back before 6, but well, I've got to be probably, because I think everybody there leaves at 5, so we got to do what we're going to do in an hour, so I'll be back probably shortly after 5. So I will have a little bit of time this afternoon back in the office. Tomorrow I've got a treatment starting at 7 in the morning, and they said it'll schedule me for about 8 hours. Hopefully it won't take 8 hours, but that puts me back home fairly close to 3 o'clock, hopefully. And if I do get home, then here's Houston's here. Let me get him marked present. Okay. If so, then I'll be able to teach, maybe if I'm wide enough awake, to teach my 3:15 class. So I'll try to get that done. But then Friday, gone again. Treatment from 8:15 in the morning until probably 4 or 5 o'clock in the afternoon. Now that's a 90% treatment, so there's not going to be much opportunity for them to speed that along. The one tomorrow is only 10%, so hopefully that will go a little bit faster. But they allow 8 hours for each of them. So this week is almost wasted. By next week, hopefully things will be better. The trouble is, usually when I take a treatment, my hemoglobin and the stuff gets even lower, and I'm already pretty severely anemic, so I'm liable to be even lower energy next week than I am this week. But at least the memorial service will be over with. Most of the work in her apartment will probably be that I have to do anything with will be through. So hopefully we will be on, and that will be, those kind of things will be over. Okay. Now, if that wasn't enough for this week, we live in an old house. It was built in 1930. Good old house. However, some previous owner or somebody years ago put a bathroom upstairs between the 2 front bedrooms. And they probably just didn't install it properly. They didn't have quite enough fall for the septic line, so it was almost level, but it basically worked for most of the umpteen years that we've lived here. We had problems every now and then. They'd have to come in and fix it. But what appears now, we've had the same Roto-Rooter guy here for 3 times now in the last month, and they come, if it does back up again. And what he did, he brought his camera this time and found out that the house has settled just ever so slightly in the front. So whereas before it was almost level, now actually the water's having to go uphill, and water doesn't go uphill, and that's what's been causing our plumbing problems. So I had him in the middle of the morning here taking care of things. I went on and taught my first class most of the time while I was here, but he had to leave, so I missed about 10 or 15 minutes of it just to take care of him. And now the cleaning lady just got here, and she got here late. So if you hear noise in the background, that's her. And then I've got to be gone this afternoon. So it's when it rains, it pours, but all things will pass, hopefully. Hopefully y'all will pass anyway. Never mind. Okay. As in pass the course. Okay. So any questions, issues, problems, concerns, anything you want to bring up before we get into calculus? Okay. If not, we're in chapter 11, vectors in the geometry of space, and we're in section 11.3, the dot product of two vectors. And example 5 is building on what we talked about last time. Now, what we have here, it says find the vector component of vector u. If I could get my pen to show up somewhere, here it is. Vector u, which is, now this is in 2 space, the plane, okay? 5, 10, those are the components of your vector in 2 space on the plane. Find the vector component of this one that is orthogonal to vector v, 4, 3. Okay, given that W1, okay, is the projection of V onto U, believe I'm saying that right. No, I'm sorry, projection of U onto V. Projection of U onto V, and they give you that as 8, 6. Now, why they did that, I'm not sure. Okay, I guess just to make it a little easier. And that this U that we're talking about here, 5, 10, of course, is going to be the sum, the vector sum of W plus W1. So they've really done all the work for you. Okay, all it gets down to here is, now, I have they not given you us the formula? No, I guess they haven't given us this formula yet. That's why they did it. That I understand now. Okay, I thought we had already had this formula. So basically what we know is this right here. U is equal to this, and that's equal to W1 plus W2. W1 is the projection of vector U onto vector V. So that means that's the component of U that's parallel to V. So that means that's W1. W2 then is a component perpendicular to V. So therefore that's what we're looking at. We call it orthogonal to V. So basically all you have to do is plug and chug here. If you can plug. Okay, here we go. 5, 10, the vector 5, 10 is equal to the vector W1, which is right here, 8, 6 plus W2. That's not what you get for your income taxes. Okay. Now, so what you do, subtract this from that. So 5, 10, that's a pretty ugly angle bracket, isn't it? Minus 8, 6 is equal to W2, and W2 is exactly what we're looking for here. So this will be, anyone do the math? Negative 3, 4. You don't have to draw any parallelograms or anything else. Just do the math. Component thing. That is your vector W2, which is the vector. Oh, here comes Jesus Miguel. Okay, let me get him marked here. Okay. Good deal. We're up to 5 students now. We're more than half of the class. Hopefully the others will be coming in too. There's your answer. Negative 3, 4. Now, how did the book do? They got it too. Good for them. Any questions on what I did there? Again, they did the heavy lifting here. All we had to do was vector subtraction. That was easy. Next page, we're going to see how to do the heavy lifting. So any questions before I erase this? Is this somebody else coming in? I think it is. I can't see who it is. Yuck. He just came in without my being able to read who it is. James is here. Okay. So James is here. So the middle part of the alphabet pulled ahead of the back part of the alphabet, and the top of the alphabet is trailing kind of badly here. So, but anyway, glad y'all are here. Missing 2 now. Okay. All right. I'm sorry. I was cramming down as much lunch as I could in the few minutes I had between my last class and this class. It's just been a horrendous day. Okay. So, what I was trying to do is find, there we go. That's why sometimes I can't find these things. They get hidden below that taskbar. So anyway, let me erase the ink on the slide, and let's see how they do it. Because U is W1 plus W2, which they give us right here, where W1 is parallel to the vector V, it follows that W2 must be the vector component that's perpendicular or orthogonal to V. So all you have to do then is say W2 is equal to U minus W1, plug in what U is, 510, subtract from it 86, and that gives you negative 3, 4. Exactly like we did, probably not quite the same order of steps, but same result. Any question on that? Does that make sense? Okay, now we move into how in the world did they get that in the first place? Okay, that's what was sort of confusing to me. Why are they giving you the answer? Well, because they haven't shown you how to get the answer yet. Oh, wait, before we do that, here's the picture of example 5. To see that W2 is orthogonal to V, shown here, here is vector U, 510. There's vector V, 4, 3. The projection of U onto V is this W1 here, which happens to be 8, 6. Okay? Now, the other component of this is the component parallel to V. The other component would then have to be perpendicular to V, and then by this you can see this minus that equals this. In other words, if you took this vector here, drew the negative of that from here, there you have it back here at negative 3, 4. Does that make sense? Okay. Now, how did they do it? Here's how they do it. Here's the theorem. The projection using the dot product. If U and V are non-zero vectors, by all means, do not mess around with the zero vector. It's, I want to say almost pretty useless. There are purposes for it, but we don't want them here. U and V are non-zero vectors. Then the projection of U onto V, that's what we're dealing with, projection of U onto V. That would be the component of U parallel to V, other way to say that, is the dot product of U and V divided by the magnitude of V squared, which if you remember, that's V dot V. Remember? That's the magnitude of V squared. But it's in the direction of V, so we multiply then again by V. See, this is a scalar, that's a scalar, this is a projection, which means a vector. It's the vector in the direction of V. Now, how do we do this? Well, V over one of these, magnitude of V, that's the unit vector in the direction of v. So that gives you that unit vector, the direction, the u dot v over magnitude of v. That gives you the projection. Okay, so basically the magnitude of u dot v over, the dot product of u dot v over the magnitude of v, just one of them, that gives you the magnitude of the vector, and then v over magnitude of v, that's the unit vector in the direction you want it, and that gives it to you. So the projection of u onto v can be written as a scalar multiple of a unit vector, that's the v over v, magnitude of v, in the direction of v. That is, and this is what I was just saying, I didn't know they were going to say it here too, the u dot v over magnitude of v is the magnitude of the projection. V over magnitude of v is the direction of the projection. So basically you could think of that as a k, and that k is then this. Well, what is that? Okay, if you think back on it, I'm just going to refresh your memory here, hopefully. Another definition, remember this one, that of u dot v is equal to magnitude of u times the magnitude of v times the cosine of the angle in between. Okay, now if you were to divide this by the magnitude of u, magnitude of v, okay, then this disappears and you get u times the magnitude of u times the cosine of theta. So that's another way to express that magnitude of your projection in the direction of v. The scalar k is called the component of u in the direction of v. And that would be, oh, here comes Esther. Good deal. Okay, so Esther's here. We're only missing Jemanuel. So hopefully he'll be coming in. It's so much nicer and more satisfying and easier to mark everybody present than to have to put some absences there. So I'm so glad y'all are here. And I like to see you too, of course. Okay, now, so here's several ways to express that. The projection of u onto v is either this formula here, or the k, magnitude of u times cosine of theta, times the unit vector. Okay, that's another way to express it. So there's several different ways to show that and to do it. Okay, so scalar k is the component of u in the direction of v. Okay, for some reason this won't advance. Okay, so here's example 6, middle of page 775. By the way, I didn't say that, Esther, when you came in. We're in chapter 11, vectors in the geometry of space. 11.3 is the dot product of two vectors on page 775. We're on example 6 right now. So find the projection of u onto v and the vector component of u orthogonal to v, similar to what we just did. For now we're in 3 space. Last problem example we were in 2 space, now we're in 3 space. Okay, so they're first asking for the projection of u onto v. Okay, that is the component of v in the direction, component of u in the direction of v. I can't talk. Okay, so what are we going to have to do? That projection of u onto v. Okay, now got a couple formulas you could use. I wouldn't try to use the cosine formula. We don't have a cosine visible here, so forget that one. Let's do what we know. What we know is the dot product of u dot v over the magnitude of v squared. Now it sort of puzzles me why they won't go on and say that is also, and I'll refer you back if I can find it quickly. I don't do anything very quickly. There it is. If you go back to page 770, the theorem 11.4, properties of the dot product, v dot v is magnitude of v squared. Now, frankly, to me, that's the easy way to calculate it. So I'm going to do that just because I'm sort of lazy. I like the easy way to do things. So I'm going to call this v dot v. Okay. Okay. And I think that would do it. Oh, and this is a number in the direction of the angle v, of the vector v. All right. So let's do that numerator. The numerator, the dot product, is product of the like components. 3 times 7 is 21, plus a negative 5 times a 1, so that would be a minus 5, plus 2 times a negative 2, that would be minus 4, divided by v dot v, which would be 49, that times itself, plus 1, plus 4. Okay, that one's always going to be positive, by the way. Okay, and then you multiply that by the vector v. I'm not going to write all the vector out. Let's see what we've got here. This is 21 minus 9, I think is 12, divided by 54 times the vector v. I'll come back to that in a minute. 6 will go into 12 twice. 6, well, actually, no. Okay, 6 will go into 54 9 times, so it's 2/9 of vector v, which would be 14. Is it all right with you if I go on and write this in component notation? Okay, 14 over 9, that's 2 times 7 over 9, comma, 2 over 9, that's this thing times 1, comma, and then 4 over 9. So there is the projection of u onto v, or the component of u in the direction of v. There it is. Okay, so that answers the first part. That's it right there. Okay, the second part says, and you can write this in IJK notation as well, 14/9 I plus 2/9 j plus 4 9 k. Okay, I was just a little surprised that all came out positive. Okay, no, it didn't. I knew there was something wrong here. This is a minus 4/9 here. I forgot my minus sign there. It's 2/9 times a minus 2, that would be a minus 4/9. I thought that doesn't seem right. Okay, now it is hopefully right. Okay, now the second question said, what's the vector component of u orthogonal to v? Okay, we know that this is a component parallel to v. The one orthogonal to v, if you do this component plus the one we're looking for, you get u. So you do u minus this one, 14/9, comma 2/9, comma, negative 4 nights. Okay, which will be, I'm going to write U in this same notation, 3, comma, negative 5, comma, 2, minus 14 nights, boo hiss, 2 nights, comma, negative 4 nights. Okay. Now this is kind of a messy subtraction, but it is quite doable. 3 would be 27 nights, right? 27 nights minus 14 nights, I'm pretty sure would be 13 nights if I can find my pen. 13 nights, comma. This will be negative 45 nights, minus 2 would be negative 47 nights, comma. And this would be 18 nights minus a minus, which is plus 4 nights, is 20. Goodness, my old gray cell's not working too well today. 22 nights, I think. Great day. My thinking is not doing well. All right, let's see what we got. They put it in IJK notation. Since I'm writing with an ionizing pen, I'm going to do all I can to do it as concisely as possible. Okay, so the first was 14 nights I plus 2 nights J minus 4 nights K, just like we got. And the second was 13 nights I minus 47 nights J plus 22 nights K. Yes. Okay. Now that's how we did it using component notation. They used IJK notation. Let me see if y'all are scooted as far to the right as you can be. No, you're not. Let me scoot you over there. Kyle, you're kind of in the way. Okay. Let me clear this off the screen. Okay. And let's see how they did it. Okay. The projection of U onto V, and they like to call that W1. I'm not really sure why, but that's perfectly fine, is equal to the dot product of U dot do, U dot V, and like I like to call it, the dot over the dot product of V dot V. Okay, that is magnitude of V squared. So to me, that's an easier calculation than this is, but it's still pretty easy. Times the vector V. Okay. Well, what does that give you? Without showing how they did it, they did 12/54 times this vector V. Well, we can certainly reduce that 12/54, and they didn't show how, but boy, they're skipping steps like crazy. They divided 6 into both of those, and that gave them 2 nights times 7 would be 14 nights. 2 nights times 1 is 2 nights J, and 2 nights times a negative 2K would be negative 4 nights K. Okay, so there's your answer to the first one, the projection of U onto V. Now, the vector component of U orthogonal to V would be then to take the U minus the W1 we just calculated, and that would be 3I minus 5J plus 2K minus a 14 nights I plus 2 nights J minus 4 nights K. And I admit this isn't much different from what we did, but you just had to write so many extra letters like I, J, and K twice, you know. So why not do it in component notation? It just makes it easier. And that gave you 13 nights I, which is basically 27 nights minus 14 nights I minus 45 nights minus another 2 nights, that's minus 47 nights J, and 18 nights K minus 4 nights K minus a minus, which is plus 4. 18 plus 4 is 22 nights K. All right. Any questions? Same thing we got. And here's the figure. Wow. 3 space is so hard to draw and visualize. So if you're, hey, perfect attendance today again. Way to go, team. You beat the first class. You had already beat them. They only had 3 out of 4 present. Y'all have 100% present. Way to go. That makes it perfect attendance for the week. So way to go. Okay. Now, here's what we got. Vector U, which was 3 units on the x-axis. There's one, nope, these are 2 units each. So there's 2.5 would be 3 units here. That corresponds to where that is on the x-axis. Minus 5j, well, this is minus 2, minus 4, minus 1 more would be 5. That corresponds to where it is on the y-axis. And then it says plus 2k. Well, 2k would be this much up here. So you go from this point here, that same distance up here. There's your point, your terminal point for U. Okay, with U being initial point of the origin, which is the best place to write them. Now, I don't see that they even drew the vector V on here. Do y'all see it anywhere? Oh, there it is. Okay, there's vector V. So vector V was, and it's not on the screen, so let me look in the book, 7i plus j minus 2k. So you go out here 7. 2, 4, 6, and a half more would be 7. So there you are on the x coordinate. Plus j. So if this is plus 2 here, plus 1 would be there. Ride that up here parallel to the x-axis, and there you have the j component. And then you have a minus 2k. So that same distance you went up before, you go down from that point here. And that's really hard to see with this black box in the way. So I'm going to sort of wait, hoping it's going to fade away in a second. And what we do, we go down 2k from this point here. And that looks to be about correct. So there's the component V. So the vector component of U onto V would then be, sorry folks, the anemia is kicking in big time here. Wait. I hate having to do that in class, but boy, I'm losing consciousness here almost. Here is vector U in this direction. We want the project that down to the perpendicular to V here, and this would be that W1, a very small vector here, because these were pretty close to being orthogonal, not quite, but they were getting close. So that's a very small projection here, which means the perpendicular component of that adds up to here still won't be as big as U, but close to it, and that's your W2, and that's what we're looking for here. And that's a substantially larger number. The X component is just about the same for both W1 and W2. The Y component is positive for W1, this one, not very positive, but positive. Very large negative component here, so that's why you're way out here. And then your W1 is only 4 nights here. So from, if they had plotted this point here the way they had the other, but it's really hard and it gets so confusing, you're not going up so far here. Okay, or actually this one is going down slightly. Okay, minus 4/9. So less than half downward. Okay, and then this one winds up being same, almost the same x, way negative on y, and up more than 2 spaces on z from where that would have been in the xy plane. So hard to visualize this on 3 space because you're drawing it on a 2-dimensional plane, sheet of paper, okay, or surface. So it's so hard to get the perspective you need from it. Any questions before we move on? Okay, if we can move on. Okay, all right, they're skipping example 7, so we're not going to move on. We're just going to pull out our pad, our pen, and do example 7. This is one a lot like one we had earlier, an example earlier. So what I'm going to do is go back to the picture we had before, so I don't need to draw it. Don't tell me they don't have the picture. They don't have I gone far enough? Let me go back a little further. Ah, there it is. Okay, not the same picture, but similar. Okay, now they're telling us this is a 600-pound boat. So that is your weight going straight toward the center of the earth. So this, if I can get the pen to show up here somewhere, there it is. That's your force here, your weight. This is 600 pounds toward the center of the earth. That's the magnitude of that vector W. Oh, F, I'm sorry. It sits on a ramp inclined at 30 degrees. Now this is not a 30-degree incline, but let's just imagine it is. Let's just imagine this is 30 degrees. Okay? Okay? It's not. It's less than 30, but we'll just imagine that's 30. Sort of shown in this figure. What force is required to keep the boat from rolling down the ramp? So in other words, what force do you have to pull in this direction to keep the boat from going downhill? Okay, that's the question. Oh boy. Okay, now what we're going to do here, and I did all this geometry before for you, so I'll just sort of remind you of what's going on here. Let's just look at this little, if I could get the pen to show up here, where is it? There we are. Okay, let's just look at this little triangle here. Okay, with that being your 90 degrees here. Okay, this is 30 degree. Now, well, you know this isn't 30, but this would make this 60 degrees. Okay, we know that's 60. With that angle 60 and this is 90, then this angle right here also has to be 30 degrees. Okay, now, yeah, we're looking for the component that you would have to have holding the boat up the ramp to keep it from sliding down. That has to be exactly equal to your W1 here. So that would be the projection of this vector, 600 in the minus y direction, onto the ramp here. Okay, now the trouble is we don't know okay, how to say this, we really don't need the projection. I'm sure they're going to use the projection. Let's just use what we know. Okay, just looking at this triangle here, basically we're looking for this component right here. we're just going to flip it around and pull it that way. So we're going to take the negative of this component right here. Okay, well, here we know this side right here is 600 pounds. This is 30 degrees. This side here, the sine of 30 degrees is 1/2. So this component here is going to be 300 pounds. And guess what? That's the component here, 300 pounds. Now, I'm sure how they're going to do it is a lot more complicated than that. This one, you just see it right there. Let me make sure I did it right. Yeah, 300 pounds. They dealt with the vector v. This is what they called the vector v. Not really sure why. Okay. And they did f. And by the way, they had to break this into the x component here is the square root of 3 over 2, and the y component is 1/2. Okay, that would be what those relative components would be. And they dotted that one with the force vector here. And it just, they just went around their elbow to get to their ear, just trying to use their projection. So much easier just to do the physics on it. This is the force component that you're having to work against. That's 300 pounds. That means this has to be 300 pounds. I don't see any reason to belabor that any more. Okay, so let's move on. Okay, so let's go back to where we were. Was that okay? I should have asked that question. Any questions on that before we leave it? Just seemed like that was unnecessarily complications to go through all that when all you had to do was calculate this component here. Once you get that, you know that has to be the component you have to pull up with to keep it from rolling down. Okay. All right. Oh, we're going to see how they did it. So here we go. Okay. I was thinking this was one I was doing, but that's how they did it. So your force vector is W1 plus W2. The weight, W1 is the weight down the ramp. W2 is the weight perpendicular to the ramp. W1 is the weight pulling the boat down the ramp. Oh, wait. This is the other problem, isn't it? Yeah. Sorry about that. I didn't think this one was on there. I forgot I was there. Okay. We're looking for work now. Isn't that everybody? Okay. All right, here we go. Work. Page 776. All right. The work W done by a constant force acting along a line of an object. That's a really strange way to say it. Along the line of an object. What is the line of an object? Okay, we'll talk about that. Is given by work is equal to the magnitude of the force times the distance. Okay, now here's what they mean by that. If your force is parallel to the displacement of the object, that's what we got. Force times distance. Magnitude of force times the magnitude of your displacement, PQ. Okay? Now, the force that acts along the line of motion. That's the only part of the force that does act on it. If you had done a force up at an angle, only the component along the line of motion is going to be acting on it. Okay? So, when the constant force is not directed along the line of motion, you can see from this figure, and my ceiling fan is getting a bit too cool. I don't know why, but I'm going to turn it off for now. It may have to turn it back on later, but sorry about that. When the constant force is not directed along the line of motion, but is at some angle to that motion, you can see from this figure that the work done by the force is the projection of that force onto your direction of your movement, PQ, and that would be the cosine of this angle, remember that formula, times the magnitude of F times the magnitude of that vector PQ, okay? Which, by the way, is just F dot PQ. Why go through all this? There's the answer, okay? The force acts at an angle theta with the line of motion. Now, if you know the angle theta and you don't know the formula, then, well, do what you have to do, okay? This notion of work is summarized in this definition. The work W done by a constant force F at its point of application moves along the vector, this is a rather strange way of saying it, VQ. Now, as its point of application moves along the vector PQ, okay, didn't work with at in there, okay, is one of the following. It's either the projection of the force onto that PQ times the magnitude of PQ, or you can look at it this way, F dot PQ. Okay, that's it. Pretty simple. So here's an example. I'm going to need another swig of something. I'm losing my voice. Okay. To close a sliding door, a person pulls a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Okay, as shown in this figure here. So this person is pulling, walking along here, keeping the angle at 60 degrees and constantly giving a force of 50 pounds on that rope. Okay, the question is, find the work done in moving the door 12 feet to its closed position. So it's 12 feet from here to there. Okay, so now they want to use a projection, which is perfectly fine to do, but it just seems like to me it's so much easier since we know this force here, right here, this force here is 50 pounds. Okay, now if you just took the component of that force in the direction that you're trying to move the door, okay, and that's sort of hard to see in thing because everything's red, but there it is. That projection here is going to be, okay, this is a 30 degree, 60 degree, 90 degree. This short side over here is exactly half of your hypotenuse, and your hypotenuse is 60. Okay, so therefore half of 50 pounds is 25 pounds. Okay, that's the projection here in that direction. Okay, now that is in the direction of the motion. 25 pounds times your 12 feet. That would be a 0, 50, 20, 25, 300. Okay, 300 foot-pounds. All right, that's all you have to do, okay? They want you to use that projection formula. Let's watch them do it, okay? Let me make sure I did it right, though. Yep, 300 foot-pounds. Wow. The projection of the force onto PQ times the PQ, that's the work, okay? Cosine 60, 1/2, times your force, same thing, the force of 50, multiply it by 12, and you got, that's the magnitude of PQ, and I think I would do it just half of 12 would be 6, 6 times 50 would be 300. Whoa, they didn't give an answer. Okay, the answer is 300 foot-pounds. Rather bizarre, they just stop it there without giving an answer. I guess they left the rest to the student. That's how they usually phrase it. All right, that finishes 11.3. Any questions on 11.3, the dot product? Okay, always look at your concept chat. Okay, pay attention to that. Be sure you understand that. Go for it. Homework exercises then would be any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 17. They're all at Calc Chat. 13's at Calc View. 19 is both at Calc Chat and Calc View. 21 to 25 are all at Calc Chat. 25 or 27 are both at Calc Chat. Any of the odds 31 to 35 all at Calc Chat. 31's at Calc View. Any of the odds 37 to 43 all at Calc Chat. 37's at Calc View. 45 or 47 should both be at Calc Chat. 49 should be at Calc Chat. 51 or 53 should be at Calc Chat. And any of the odds 55 through 61 should be at Calc Chat. Okay. '63 should be at Calc Chat. 65 or 67 should be at Calc Chat. 69 or any of the odds 69 to 75 should be at Calc Chat. Now that very last one, it says prove the Cauchy-Schwarz inequality. Well, I don't care if you prove that or not. That's up to you. Pretty good exercise to do it, but I'm pointing it out to you because there's at least 3 potential paper topics. Who was Cauchy? I think we've run into his name before. Who was Schwarz? Don't usually run into his name. How did they develop this? Were they working together, working separately? Did Schwarz add to what Cauchy had done? I don't know. Anyway, who uses this? What's the end result? I mean, why have it? How is it useful? Okay, now that does end the PowerPoint for 11.4. So let me click on that to discard my ink, and we'll get out of that. Our screen sharing has stopped, and we'll go to 11.4. Okay. Goodness, my head is hurting like crazy. I'm going to try to move this taskbar down and away, and we'll go from current slide here. Hold on just a minute. Goodness gracious. I have a burning behind my eye. I don't know what that is. Let me get something else to drink here. Okay, let's go from current slide. We're still in Chapter 11, Vectors in the Geometry of Space. 11.4 is now talking about the second way to multiply two vectors. The dot product gave us a scalar quantity. The cross product gives us a vector quantity. The cross product of two vectors in space produces a vector. Now you can have dot products in a plane. You cannot have cross products in a plane. You can multiply two products together in a plane. The vector is going to be perpendicular to that plane. So basically this is a spatial characterization only. Dot products could be on the plane or in space. Cross products only in space. Three dimensions are automatically involved. So our objectives here are find the cross product of two vectors in space and use the triple scalar product, we'll have to define what that is, of three vectors in space and see what practical applications we have of that. Okay, so what is the cross product? Many applications in physics, engineering, geometry, maybe other fields, involve finding a vector in space that is orthogonal to two other given vectors. So let's say you have two vectors here, any angle whatsoever, they define a plane. Any two lines defines a plane. Okay? A cross product then is going to be perpendicular to that plane, orthogonal to that plane, orthogonal to those two given vectors. In this section we'll study a product that will yield such a vector. Is called the cross product. It is most conveniently defined and calculated using the standard unit vector form. Okay? I guess I'll buy that statement. Because the cross product yields a vector, it is also sometimes called the vector product. Okay? Now, you might ask yourself, well, why didn't they call a dot product a scalar product? Well, they already use that name to mean the product between a scalar and a vector. That's what they mean by a scalar product. And I can remember some older texts that refer to a dot product as a scalar product, but that gets so confusing, so we don't do that. We just say the dot product, a scalar product, which is scalar times a vector. Dot product is a vector dotted with another vector that produces a scalar, but a cross product is a vector multiplied by a vector that produces a vector, and that's called the vector product or the cross product. So here is the definition of the cross product of two vectors in space. So let U be U1i plus U2j plus U3k. I would have become that angle bracket U1 comma U2 comma U3, but that's me. Close angle bracket. And vector V is V1i plus V2j plus V3k, or angle bracket V1 comma V2 comma V3 close angle bracket. Let those be two vectors in space. The cross product of U and V is the vector U cross V, and oh my goodness, what a mess. U2V3 minus U3V2 in the I direction minus U1V3 minus U3V1 in the J direction plus U1V2 minus U2V1 in the K direction. Do I have to memorize that? I sure hope not. I'm no good at memorization. I'll always get something screwed up. So I'll show you in a little bit an easier way to do this. It is important to note that that definition applies only to three-dimensional vectors. It does not apply to two-dimensional vectors. Okay, it's pretty easy to do a two-dimensional vector. If the two-dimensional vectors are in the xy plane, the cross product is in the z plane, is a line in z, not have a component in either of the x or the y component. Okay, so here's the convenient way to calculate that, to use a determinant form with a cofactor expansion shown here. Okay, now they do it the hard way. Okay, I will show you a little bit easier. I think they'll get around to showing it too. Okay, if you do u cross v, what you do in the first row of that determinant is put your unit vectors I, j, and k. Okay, and then what you do in the second row is put those components, the I, j, k components of the first vector listed here, u, u1, u2, u3. See, everything works better if you deal with component form. And the third in that matrix will be v1, v2, and v3. v1i plus v2j plus v3k. Okay, so there's your third row. You have a square matrix there, 3 by 3. You can take a determinant of that. Okay, now how do you do that? All right, you could pick any row, any column. The easiest one to do is the top row, I, j, and k. For the I component, wipe out the first row and first column where that I11 is, that element, the 1,1 entry in that matrix, and then do a cross product, a determinant here, u2 v3 minus v2 u3. That's it. Okay, and you can usually do that in your head. That's time that I that you had here. Okay, now why the minus sign here? Let me explain that to you. When you do it, this is what they mean by cofactor expansion. When you're doing this, think of this as a plus entry. Always the upper left is a plus. Then start counting any direction here. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Or plus, minus, plus, minus, plus, minus, plus, minus, plus. Or plus, minus, plus, minus, plus, minus, plus, minus, plus. Any way you do it, they're all going to have the same sign. Well, you're going to j next. That was in a negative position. Plus, minus, plus. So put a minus sign down for in front of the j. Wipe out its row and column. Its row is the same row. Wipe out its column, and then you have u1 v1 minus v1 u1 u3. I'm sorry, u3. Okay, sorry a minute, I'm losing my voice again. Yeah. Okay, then we move to the k. Plus, minus, plus. So this is a plus k. Plus, wipe out the first row. You already had it wiped out. Wipe out the third column, and then do the determinant here. u1 v2 minus v1 u2. That's how you came up with this, without having to memorize it. Okay? Without having to memorize it. Now, you just have to remember, you wipe out row and column of that one, and take the determinant of what's left, wipe out the row and a minus sign here, wipe out the row and column, take the determinant of what's left, wipe out the row and column here, take the determinant of what's left. Okay? This is the first and the last are plus, the middle is minus. Okay. They just show you the results of that. Goodness gracious, I'm losing it. Okay. Note the minus sign in front of the J component, and each of the three 2x2 determinants can be evaluated using the diagonal pattern. It's always the product of the main diagonal, upper left to lower right, minus the product of the other diagonal from lower left to upper right. So it's AD minus BC. Always the minus going up. Now here's a few examples. 2, 4, 3, negative 1, be minus 2, minus 12, which is minus 13. This one, 4, 0, minus 6, 3, that would be 4 times 3 is 12, minus a minus 6 times 0, minus 0. So, yep, that's the solution. Now, just how you do matrices. Okay, so here's example 1. Let's do a few cross products. All right. My goodness, I'm losing energy fast. Of course, part of it is I only got about half of my lunch eaten, and that's probably why. Now, I'm going to show you what I think is the easier way of doing this. So you don't have to remember that minus in front of the J. It's pretty straightforward, and you probably know this from physics, possibly. So U cross V, okay? That would be the determinant of this matrix here. Always the top row, I, J, K. Now remember, I put a hat on my unit vectors. You put the components of the one that's listed first, that's the U, that would be 1, negative 2, 1. Then put the components of the one listed second, the V, 3, 1, negative 2. Now, here's where I cheat, okay? Okay, I'm going to erase this line here. I thought I was going to erase that line there. There we go. All right, and you've probably seen this and done this before, but if not, here it is. Repeat the first two columns. I, J, 1, negative 2, 3, 1. Now treat that as a matrix. Now, number one, you cannot take the determinant of a non-square matrix. We're sort of like we're taking a determinant, but here's what we're going to do. All we're going to do are your diagonals. Remember, every down diagonal is positive, okay? So this will be a minus 2 times minus 2 is plus 4i. So that's 4i. Do the down diagonal here. That's plus 3j. You don't have to worry about plus minus, that kind of stuff. Just do it. 1 times 3 is 3j. Plus 3j. Then do the down diagonal here, and you have plus k. Okay, you're halfway through. Now I'm going to erase my construction lines there just because they get a little messy looking. So I'm going to erase that one, and erase that one. Okay. Now I'm going to do my up diagonals. Just like we said in the 2x2s, you do the same thing here. Okay. Only any up diagonal is going to be the negative. So it's going to be minus 2 times the negative 3 is a minus 6. Well, minus times minus is plus, so that's plus 6k. Now notice I'm writing them like components, okay? Then let's do this one. It's an up diagonal, so it's minus. 1 times 1 is 1, and that's I, so it's a minus 1i. And then we'll do this up diagonal, and that's a minus also. Minus times a minus is plus. 2 times 1 is 2. So plus 2j. And then add them together. 3i plus 5j plus 7k. Rather odd, isn't it? Okay. That's what we get for U cross V. Okay. I don't know if you find that easier. I do. To me, that's a lot less writing than that is. Okay. And you don't have to worry about remembering the minus sign for the J. You just do expand it, the first two columns, and then treat it just down diagonals, down diagonals, up diagonals. Okay. Now let's do V cross U. Okay. V cross U. That would be like a determinant. Okay. And again, the top row is I, J, K. Okay. I'm going to repeat my I and a J. I just know I'm going to do it, so I'm just going to go on and do it right off the top. Then put my V components. 3, 1, negative 2, repeating 3, 1. Then do my U, 1, negative 2, 1, 1, negative 2, 1, and repeat the first two, 1, negative 2. Okay. Now, let's do our down diagonals like we did before, and that would be just an I. Down diagonal here is going to be a minus 2j. Down diagonal here, minus 6k. Okay, I'm going to erase my construction lines just because they're a little messy. I'm sure y'all are shocked to hear that anything I do is messy. Okay. Now let's do the up diagonals. Remember, they're always negative. That's negative k. Up diagonal here. That would have been a plus 4i, but because it's up diagonal, that's going to be a minus 4i. And then minus 3j. And then when you add those together, you get a minus 3i, minus 5j, minus 7k. Not only is that a little odd, but it's very negative. It's exactly the opposite of this one. So guess what? Cross products do not commute. In fact, they anti-commute. They produce the negative of the other. So if you know one cross product, all you have to do is do the negative of that vector to get the other cross product. All right. Kinda handy to know. Okay. Now our next one is saying V cross V. So I'm going to erase all the ink. Does anyone need this a little longer? Let's make sure they got it right in the book. We don't want them to make a mistake, do we? Okay. They got 3i plus 5j plus 7k minus 3i minus 5j minus 7k. Okay. Let's do the third one, the C. I think this is going to be about all for today then. To do a cross product here, if I could get my pen to show up. Has anyone seen it yet? Where are you, pen? There you are. Okay. This is going to be kind of like a determinant with I, J, K across the top, and repeat the I and the J. That's not really right notation, but I'm going to do it. V dot V would cross V would be 3, 1, negative 2, 3, 1. Repeat those first two. 3, 1, negative 2, 3, 1. It's V crossed itself. Okay, let's go for it. That would be a minus 2i minus 6j plus 3k. Okay, that's our down diagonals. Now we have to do the up diagonals, which are, of course, all going to be the negative of whatever it would have been. Okay, so let's get the up diagonals here. And that would be, it would have been a 3k, but since it's up diagonal, it'd be a minus 3k. And you go this one, that would have been a minus 2i, but you do the negation because it's going uphill. That's a plus 2i. Again. And then you do this one, which was a minus 6j, but because it's going uphill, you make it the negative of that, which is a plus 6j. And guess what, folks? That gives you your good old zero vector. I would rather have written that 0, 0, 0, or just written it bold 0. If you can write bold, I can't, so I put an arrow over it, the zero vector. Okay, now let's talk about a couple things now. Remember, in cross products, the cross product of two perpendicular vectors is always 0. Okay, the dot product. Two perpendicular vectors, always 0. But if you dotted a vector with itself in the same direction, you just basically, it's a straight multiplication. You just, you get the maximum value out of that one. Now, let's look here. What if you cross two vectors that are perpendicular to each other? You get the maximum value, but in the plane perpendicular to those two. Okay? But if you cross two vectors that are parallel, like vector v with vector v, always 0 vector. Now, it's not just the number 0, it's a 0 vector. Okay? Now, I think that ran us out of time, didn't it? Yes, it did. In fact, a minute over. So we will pick up on the box wait. Let me just show you how they did theirs. Sorry, I meant to do that before we left here. So let's erase this. Okay. U cross V, they did it. Expansion, certainly fine to do it that way if you like it. And that gave you that, which gave you that. Same thing we got. I think they did a lot more work to get it. I'm lazy. B, looking at that, expanding again, multiplying, see what you get, adding, and you get exactly the negative of part A. And then when you did V cross itself, you got the 0 vector. Whoa, they didn't show you any work there, but sure enough you did. Okay? Now, this is where we'll pick up next time, on page 780. Okay? Let me go to the homework exercises. I think you could do either 3 or 5. They're both at Calc Chat. You can do either 7 or 9. They're both at Calc Chat. 7's at Calc View. You can do 11 or 13. They're both at Calc Chat. And I think that's where we stop. Okay? I believe it is. If not, you can stop there anyway and we'll pick it up and go from there. Okay? So, not too many in 11.4, plenty in 11.3. Any questions? All right. So, folks, if you're looking for me most of the rest of the week, now, Kira, James, and Jemanuel, I think it is, no, Kira, James, and Jesus I'll see you in about a half hour. Okay. The rest of you, have a good weekend. I will be out of pocket just about the rest of the week. Okay. Wanted to go eat lunch, finish my lunch now. Then I'll have my uh, differential equations course with Kira, James, and Jesus. And then I'll be heading to Episcopal Place, and it's just going to eat up most of the rest of my time. Tomorrow and Friday, I'll be almost all day, both days, at the clinic. If I get home on time on Thursday, I'll be teaching a class, but I won't have much time in between getting home and teaching the class, and it'll go way into the evening, probably. Okay, if I can make it that long. So be safe, be careful. See 3 of you in a few minutes. The rest of you have a good weekend. Guess what? No matter how pretty it is outside or anything else, the virus is still there. Okay? Please be careful. Take care. See you next week or in 30 minutes for the 3 of you. Bye-bye. Any questions before I leave? Okay. For any of you who did want to take that Physics 218, they have finally opened the course with an instructor. It's been open with no instructor. After begging, pleading, and persuading, finally someone got to somebody and they put an instructor's name on it, Dr. Bryant. So he will be teaching that class beginning tomorrow. Okay? Take care. See you either later or next week. Be safe.